the pre-lab for Chemistry 231 Lab 6, and the title of the lab is How Can an SN2 Reaction Be Used to Synthesize a Drug? And so the SN2 reaction is something we've been talking about a lot in class, and recall that that stands for substitution, nucleophilic, and the 2 stands for the fact that it is a bimolecular reaction, meaning that both the electrophile and the nucleophile are present in the transition state of the reaction. So here's what we're going to be making. We're going to be making this molecule right here, which is called phenacetin. Phenacetin is a drug. It was a pain reliever, and it was used from 1887 to 1983, so that was a good long run, almost 100 years, and it was taken off the market because it caused liver damage. Acetaminophen, which is actually the starting material in this reaction, is a metabolite of phenacetin. That is, it is how your body, using enzymes, breaks down phenacetin into different molecules. And this happens with a lot of different drugs. I'll talk about that in a second. But acetaminophen, if you'll notice, the difference between acetaminophen and phenacetin is right here, where you have a hydroxyl group or alcohol in acetaminophen, whereas you have an ether group and an ethyl group in phenacetin. And what's going on there is part of the metabolism process is adding things like OH groups to molecules to make them more polar. If they're more polar, then they're more water soluble and they can be excreted. As I said, phenacetin was removed from the market because it caused liver damage. If you've looked at the box for phenacetin, you'll see that it can cause liver damage too. But I mean, for Tylenol, it can cause liver damage too, but not quite as much. Acetaminophen was discovered as a drug because it is a metabolite of phenacetin. And just as a fun chemistry fact here, more medicinal chemistry fact, that's looking at drug metabolites is actually a pretty useful avenue for drug discovery. So, for example, Seldane, which was one of the earliest non-sedating antihistamines, was on the market from 1985 to 1997, and it was taken off of the market because of side effects that included some pretty severe cardiac arrhythmias that led to deaths, and it was replaced with the drug Allegra. And Allegra is a metabolite of Seldane, and what you can see here is the big difference between Seldane and Allegra is here we've taken a methyl group and it's been replaced with a carboxylic acid. And that carboxylic acid, being more polar because of the hydroxyl group and the carbonyl, is it's starting, there's a whole bunch more reactions that are going to happen as that's metabolized, but that you can see it's part of that process of making that molecule more polar. And it is now currently still on the market as a non-sedating antihistamine. Okay, back to what we're actually doing. First thing we're going to need to do this reaction is we need to have a good nucleophile. And recall that a negatively charged nucleophile is a better nucleophile. And so what we can do is we can take advantage of the fact that the OH group in acetaminophen is more acidic than the OH group in other alcohols, like, for example, methanol would be an example of that. And so it's easier to deprotonate or break this OH bond in order to form this negatively charged oxygen. So how are we going to form this negatively charged oxygen? Well, what we're going to do is we're going to add, and sodium methoxide will be able to remove this proton, and that is, fill in the electrons again. That is going to give us this negatively charged phenoxide ion. Plus, we're going to also have methanol as a product. Now, you might be asking yourself, why is it that this reaction can happen? Because the pKa of methanol is around 16. Why is it that the pKa of this alcohol is 10, or this phenol is 10? Why is it so much lower? Well, the reason is that the negative charge on the oxygen in the phenoxide ion is stabilized by resonance. And we can see this. We have 5 different resonance structures that we can draw, and we can just chase that negative charge. Gives us the first resonance structure, and then there's electron movement to give us the next resonance structure, and then we can draw another set of arrows to give us that resonance structure, and finally we can get back to where we started. So what that means is that means that the negative charge, because it is so delocalized, that stabilizes the conjugate base and gives us a stronger conjugate acid. So we can calculate delta H for this reaction, and we know it costs us 10 pKa units to break that OH bond in the acetaminophen, and we get 16 pKa units of energy. So overall, this is going to be exothermic by -6 pKa units, and so this reaction is favorable. So we can, the key thing here is that we can make this, which is our negatively charged nucleophile in this reaction. So here we have our nucleophile, and then the iodoethane is going to be our electrophile. And recall, we've got a partially positive, partial negative charge here. So what's going to happen is we are going to react like this. There's our nucleophile, and we're going to break. Iodide is our leaving group. We're going to break that bond, and that's going to give us our product. And notice we have formed a new carbon-oxygen bond. And we also have, sodium ions and iodide ions floating around in solution. But per usual, we're focusing in on the organic product of the reaction. Okay, so as we're planning our synthesis of phenacetin, we need to know what is the balanced chemical equation so that we can determine what the theoretical yield of the reaction is. And basically the theoretical yield, remember, is just how much product can be formed if all of the limiting reagent reacts. And then the percent yield is just the isolated yield that you get from the reaction divided by the theoretical yield times 100. Now, sometimes finding the balanced equation can be confusing because organic chemists might not write reactions in a way that's easy to see that. For example, here we've got our starting material and our product, and here's our other starting material, the iodoethane, but we've also got the solvent in the reaction written underneath the reaction. And we've also got one of the reactants written over the arrow. So it makes it, like I said, it can be a little hard to figure out what you're supposed to be looking at. However, what's written here is a really good thing for you to have in your lab notebook because it tells you everything that's going on in the reaction. But here is the balanced chemical equation for the overall reaction, and the key thing that you need to know is that for every 1 mole of acetaminophen and 1 mole of iodoethane, you're going to get 1 mole of phenacetin. And so when you're calculating the theoretical yield, if I were to tell you that this is going to be the limiting reagent because we're going to use iodoethane in excess, so that tells you that for however many moles of acetaminophen that you're going to have, you're going to, if all of it were to react, you can tell that it's a 1-to-1 molar ratio, so you know how much, you can calculate how much phenacetin you're going to form. All right, let's talk a little bit about what we're actually going to do in lab. This is the reaction setup. Basically, we're going to throw all of our reagents into a round bottom flask and heat them up for a bit. And in order to do that, we use something called a reflux apparatus, and you should watch the MIT video about this. I'm not going to say a whole lot about it except for because we have the round bottom flask with the condenser on top of it, it means that we can heat this reaction at boiling, and as the solvent goes into the condenser, it's going to drip back down into the reaction, so we won't boil the reaction dry. So pretty easy setup and pretty straightforward. So here is an outline of the procedure that we're going to be doing. we're going to be take a 50 ml RBF round bottom flask, and we're going to add the sodium methoxide to that, as well as 5 mils of absolute ethanol. Absolute ethanol is the kind of ethanol that has absolutely no water in it. So rather than being its 95% solution of ethanol in water, it is 100%. We're going to add to that the acetaminophen. Notice this is in millimoles and not in grams, so you're going to need to convert that to grams. Then we're going to insert a reflux condenser, and we're going to put a small amount of grease on this joint. And the reason for that is that the strong base, the sodium methoxide that we're using, can etch the joint and actually cause it to freeze shut, so you wouldn't ever be able to get the condenser out, and that's not good. Then what we're going to do is we're going to add a milliliter of ethyl iodide, and the way we're going to do that is we're just going to add it right down the condenser. I will do that for you with a pipetter. Then we're going to reflux this, heat it up for an hour. So the hour starts once the reaction actually starts refluxing. So what are some things that you can do during that hour? You can get caught up on your lab notebook. You can study for the test that's coming up this week. You can wash any dirty dishes or glassware that you have. You can take pictures of your apparatus and post it on Instagram and Twitter, but be sure that you use the hashtag RealTimeChem. Okay, after you have heated this for an hour and gotten caught up on all that stuff, what we're going to do is add 20 milliliters of water to the reaction, and we'll just put that right into the condenser as well. And what that's going to do is that's going to cause your compound to crash out of solution. So basically it's all going to precipitate at once, and it's probably, when it does that, it's going to grab a lot of impurities with it. So what we're going to do is kind of a modified recrystallization. We'll just take that reaction and heat it up, and that will dissolve all of our solid that just crashed out, and then we'll let it cool slowly to room temperature, and then cool it in ice, and that'll be like a recrystallization, so you'll have much nicer crystals that way. And then we'll isolate those crystals by vacuum filtration. We will let them dry for a few days, and then we will characterize them. So how are you going to characterize them? Well, we're going to characterize them using, you're going to take a melting point. That's easy. You will also be taking a proton NMR. You'll determine what your yield of your reaction is when you weigh your product. And then questions you'll need to be able to answer when you're writing your lab report are things about, how do you know you got phenastin as a product? So what data, how does the melting point tell you that you got phenastin? How does the H1 NMR tell you that you got phenastin? And then you want to say, okay, what kind of yield did I get? Did I get 100% yield? Did I get a 50% yield? Is it relatively low? This is a pretty high yielding reaction. But if your yield is low, you might want to think about what could have happened while you were doing your reaction that might have affected the yield. Okay, just a quick reminder, don't forget that in the pre-lab you need to have the reaction. As I mentioned, this is a good version of the reaction to have in your lab notebook. You want to have all the amounts of the reagents in grams or milliliters. You want to have, and also the moles, you want to have any pertinent information about the reagents in terms of their melting points, boiling points. You want to calculate the theoretical yield, and you want to have a plan or an outline of the procedure that you're going to be carrying out that day. And Dudley hopes that you take careful notes and have a good week in lab and get a very high yield in all your reactions.